I'm and I welcome you to my lecture series on computer and network security. In this video on message authentication, I will talk about the length extension attack, which is an attack against the SHA-1 and SHA-2 family of cryptographic hash functions. I'll also talk about the newest version of SHA, SHA3, which is not vulnerable to this type of attack. Let's start with the length extension attack. This is a type of attack where an attacker can use the hash value of a message and the length of the original message to calculate the hash value of a concatenation of this original message and a second message chosen by the attacker. Algorithms like SHA-1 and SHA-2, but also MD5 and MD4, which are hashing algorithms on which SHA is based, are of the type Merkle-Damgard, and they are susceptible to this kind of attack. The SHA3 algorithm is not susceptible, as it's not a Merkle-Damgard hashing algorithm. When the Merkle-Damgard hashing algorithm is used as a message authentication code by combining a hidden secret key with the message and taking a hash value of that, it becomes vulnerable to this attack. HMAC, which is a specific type of message authentication code based on hashing functions, does not combine a key with a message and does not concatenate them. Therefore, it is also not vulnerable to this attack. And let's take a closer look at how this attack works. Let's assume we have a message M that is concatenated with a secret key K and some padding P to create an integer multiple of the block size. And this message, this concatenated message, is split into blocks M1 to Mn, which are then hashed using the typical SHA structure. So the first block is sent through the function f, creating the intermediary hash value h1, and this is then used as input for hashing the next block until finally hash hn of block mn is considered the final hash value of the entire message. This hn can serve as a message authentication code for our message m, because only someone who knows the original key k is able to recreate this hash value. And if the message m is changed, a valid hash value cannot be generated because an attacker would not know the key k. However, with the length extension attack, this message can be appended with another message and a new valid hash value can be generated by an attacker without knowing k. Let's say the attacker wants to append a fraudulent message m- to our message m. If the attacker knows the original length of m, they can also derive the length of the padding p, and if they know the padding algorithm, they can actually derive the actual padding. They can then generate new padding so that the entire message, the concatenation of key k, message m, pad p, message m-, and pad p-, becomes an integer multiple of the block size. The hash value, which the attacker can intercept, hn, for example by eavesdropping on the network, can be used as an intermediary state to the hashing algorithm used to hash the new blocks m1- to mn-. The attacker then uses standard SHA and ends up with hn-, which is a valid message authentication code of this entire message. So as you can see, the attacker is able to generate a valid code for a message that combines an original message with an appended message without knowing k. You may wonder how an attacker could exploit such a length extension attack in real life. So let's take a look at an example of a website where you can order waffles online. And the orders are submitted through URL requests. Here you see the information that is appended to the URL and used to submit an order. Here you see the type of waffle is actually encoded in the URL as a key value pair. This URL then has a signature attached to it, which is based on a hash value of the data in the URL. An attacker, however, can override parameters in a URL by just repeating the same parameter with a different value. A web server will then just interpret this. First it will say waffle equals ego. When it encounters the same variable again, it will overwrite the value. Obviously, if an attacker just adds this, the signature is no longer valid. However, if the attacker knows the length of our key and the hashing algorithm that was used, he can intercept the URL and the signature, which are quite easy to intercept using eavesdropping, and generate the correct padding. He knows that the padding looks like this green data here, because the padding algorithm is known. He can then append after the padding this new data and use and create a data blocks starting from this point and adding the padding, the new padding. Based on the hash value of this first part up to the original padding, which is this value, the attacker can then use this as input for the last remaining blocks and generate a new signature. This signature will be valid, and the attacker does not know the secret key that was used to create this original signature. So as you can see, even in practice, this attack can be used. And as I mentioned, the newest member of the SHA family, SHA3, is not vulnerable to this type of attack. NIST launched a competition to find a successor for SHA2 in 2012, and finally, in 2015, they announced the winner, which ended up being standardized as SHA3. SHA3 uses a completely different mechanism of creating hash values. It has also different flavors, just like SHA2, where the hash code size varies between 224 and 512 bits. There's no limitation on the message size. However, each flavor is characterized by two parameters: the block size R in bits and the capacity C, also in bits. R plus C always equals 1600 bits. The security of the algorithm is dependent on the size of C, so the larger C, the more secure the algorithm. SHA3 makes use of a so-called sponge construction. A sponge construction is very flexible, as it doesn't only allow variable-sized input, like other hashing functions, but also supports variable-sized outputs, which makes it highly flexible. As input, SHA3 takes a message. This message is n bits long. Just like other SHA hashing algorithms, it adds padding to make sure that the message size becomes an integer multiple of the block size R. So we end up with k times R bits. SHA3 then splits our message into fixed size blocks, k blocks in total, each of R bits. Then the sponge construction is used, which I will explain in a bit, to generate the output. As I said, the output size is variable, so it can be any number of bits can be generated. In general, for example, for message authentication, a fixed number of bits is required, so output blocks of size R bits are generated until the desired number of bits is achieved. Then the first L bits are retained and the remainder are omitted. Let's take a closer look at how this sponge construction transforms our input blocks P0 to Pk-1 into our output blocks Z. As I mentioned before, SHA3 is characterized by two parameters, R and C. R is called the bit rate or the block size. If we increase the size of R, the algorithm will become faster as the number of blocks will decrease, and thus the number of rounds will decrease as well. Therefore, increasing the size of the capacity C will increase the number of rounds that have to be performed as there will be more blocks. The algorithm, the sponge construction, starts with an empty block of B0 bits, where B is the sum of R and C. So in the case of SHA3, this is 1600 0 bits. These bits are combined with our first block P0 and C0 bit, so that the size of this is also B. They are combined using an exclusive OR function. Then they are transformed using our iteration function f, and this is repeated, same process for each block where the output of this function f is always XOR together with the next input block until the final state S is obtained. S is R plus C bytes, or B, or 1600 bytes. Now, if the desired length of our output L is less than B, then the algorithm can end here. This is the end of the first phase, the absorbing phase. We just take the first L bits and return those as the output of the algorithm. If, however, we require more than B bits, so more than 1600 bits, we continue with the squeezing phase. The squeezing phase is named as such because it squeezes from this state bit array S, it squeezes out the output blocks Z0 up to Zn. So in every step of the squeezing phase, we take the first R bits and return those as the next output block. So each output block also has R bits. Then we take the complete state S of B bits and give that as input to the iteration function f. This is the same iteration function as used in the absorbing phase. The first R bits of that output are used as the next output block Z1. This process is repeated until enough bits have been generated to return the desired number of bits L. By omitting this part C from the return block, the intermediary final block cannot be used in a length extension attack because part of each output is always omitted. So therefore, SHA3 is not vulnerable to the length extension attack. Now we are missing just one final piece of the puzzle, namely, how does the iteration function f work? Before I explain how the function itself works, let's take a look at how it represents the internal intermediary state that is transformed and combined with each block P. The internal state is represented by a 5x5 matrix, where each element in the matrix is 64 bits. The matrix has 5 columns and 5 rows. The element, so the 64-bit lane at a certain row and column, is represented by L. So this is L04. This is the lane of 64 bits at column 0, row 4. The individual bits of each lane are represented by A, X, Y, 0, where X is the column, Y is the row, and 0 represents the identifier of the bit within the lane. So this goes from 0 up to 63. And this brings us to the iteration function itself. The function f consists of 24 rounds, where each round performs 5 transformations, referred to as theta, rho, pi, chi, and iota. Each of these transformations performs a substitution or permutation on the internal state. I won't go into the details of these different functions. Moreover, during the row step, there is a bit shift rotation of all the values based on the position of the words. So the lanes that I explained in the previous slide. Moreover, in the iota step, the internal state is combined with a round constant. There are 24 in total, one for each round, that are used in each iteration. And this brings us to the end of my explanation of SHA3. In the next video, I will talk about message authentication, which is one of the most important applications of cryptographic hash functions.